Another very important face recognition method that is called Laplacian face. This work was published in year 2005 and published in IEEE Translations on Pattern Analysis and Machine Intelligence. And you can also see the very familiar name in the author list, Hongjiang Zhang. So we see this name again. So remember we saw this name at the paper for audio analysis and also from the paper for video sharp change detection. Okay, so we can see the big contributions provided by Dr. Hongjiang Zhang. So why Laplacian phase? Okay, the goal of PCA. So we will also revisit the PCA and the FLD first. The goal of PCA is to find a set of orthogonal basis functions that capture the direction of maximum variations in the data, and for which the coefficients are pairwise decorrelated. So the orthogonal basis functions are actually eigenvector, okay, as we know before. And then LDA or the FLD, that is the feature phase approach. LDA search for the projection axis on which the data points of different classes are far from each other, while requiring data points of the same class are to be close to each other. So as we said before, we maximize the ratio of the between class scatter to the within class scatter to do these things. However, phase images possibly reside on a nonlinear submanifold. However, the PCA and the LDA effectively see only the Euclidean structure. So base PCA and the LDA are linear projection, linear transformation, because we all use the projection matrix. Okay. However, the phase images may reside on a nonlinear submanifold. That means the manifold is a geometric structure. That means in a higher dimensional space, the distribution of the phase images may be very nonlinear. Okay, so it's hard to find a linear equation to separate different classes of phase. Okay, and the researchers start to put more focus on nonlinear structure from the beginning of year 2000s. And in year 2005, this the Laplacian phase was proposed and was verified to have promising performance. So the manifold structure is modeled by a nearest neighbor graph, which preserve the local structure of the image space. So we will use the locality preserving projection to replace the linear projection proposed in PCA and the LDA to do the Laplacian phase. So let's revisit the PCA. PCA aims to extract a subspace in which the variance is maxima. So we want to maximize the variance. And the objective function is this. Yi is the sample data, sample point, and the y bar is the average. That is the average phase, and yi is the one of the phase image. And we want to find the best basis vector W, such that they constitute a space and maximize the variance of the projected sample data. So the opposite of the principal vectors W1 to Wk is an orthonormal set of vectors representing the eigenvectors of the sample covariance matrix associated with k largest eigenvalues. About LDA, While PCA seeks directions that are efficient for representation, LDA seeks directions that are efficient for discrimination. Okay, as we mentioned before. So suppose that we have a set of n d-dimensional samples. So from S1 to Sn belonging to L classes of phase. The objective function is this. This is the ratio of the between class scatter to the within class scatter. And the denominator is the projected the between class scatter of projected data. Okay, and the denominator is the within class scatter of the same of the projected data. And all this mathematical formulation has been introduced before.
Now we introduce the locality preserving projection, or call it LPP in short. LPP seeks the intrinsic geometry of the data and the local structure, and we try to solve the following optimization problem. The objective function is defined like this. Assume that yi and yj are the projected sample data in the lower dimensional space, and Sij means the similarity between sample I and sample j in the original feature space. And we want to find the best projection such that in the projected space, the distance between yi and yj and weighted by the similarity matrix can be minimized. And the possible way to define the similarity matrix is we just consider if the original data xi and the original data xj, if the distance between them is smaller than a predefined threshold, then the similarity is defined like this. Otherwise, the similarity is set to 0. Okay, so this is one way to define the similarity. Another way is if xi is among the k nearest neighbor of xj, or xj is among the k nearest neighbor of xi, then we will define the similarity. Otherwise, the similarity will be set as 0. So these are possible ways to define similarities between data points in the original space. And now the task is we try to find the best projection matrix, the best projection to make this objective function as small as possible. The parameter epsilon defines the radius of local neighborhood. In other words, it defines the locality. So remember that in the previous formulation, when the distance between data sample is smaller than epsilon, then we will have a similarity value larger than 0. Otherwise, the similarity value is set as 0. So the parameter epsilon defines the local neighborhood. Okay, and the objective function with symmetry weight Sij incur a heavy penalty if neighboring points xi and xj are mapped far apart. So the essential idea of LPP is that closer data points in the original space should be also mapped to close should be also mapped to close projected sample point. Okay, so if they are close, if they are nearby in the original space, then they should be also nearby or close to each other in the projected space. Okay. Minimizing it is an attempt to ensure that if xi and xj are close, then yi and yj should be close as well. So from this formulation, we can do some algebraic process. So this is the objective function, okay? And yi is actually the projected sample data from xi. yj is the projected data from xj, so we can rewrite it like this, and then we multiply xij into this equation, this formula, and then we separate it into two parts, and then we can rewrite it like this. Okay, we can rewrite it like this, where D is a diagonal matrix and its entries are column sum of X. So DII is equal to summation J Sji. So we can rewrite this formula into this one, and then we define X as the matrix like x1 to xn. So we can rewrite this like this, and then we rewrite it like this, where the diagonal matrix minus the X matrix is defined as a Laplacian matrix. Okay, so we can see that after all this process, we can rewrite the original objective function into this formulation. And in this formulation, there is a Laplacian matrix, and this is why the method is called Laplacian phase. The diagonal matrix D provides a natural measure on the data points. The bigger the value, the more important is. Okay, the more important it is. Okay, so we can see that the Laplacian matrix L is simply measure the variance. Okay, we can imagine that this is the Laplacian matrix describe the variance to the variance from sample data to the similarity. Okay, and to solve this problem, we also impose a constraint. We would like to make this y transpose dy is equal to 0. Okay, and then we try, if we rewrite it, we can incur this constraint. So finally, the minimization problem reduced to finding the best vector w, such that, and this w has this constraint, such that this value is minimized. So this is the objective function, and we want to find the best w conforming to this constraint. Okay, to make this value as small as possible. And the transformation vector w that minimizes the objective function is given by minimum eigenvalue solution to the generalized eigenvalue problem. So after many mathematical derivation, we can reduce this problem into a generalized eigenvalue problem, and the formulation is xl x transpose w is equal to lambda xd x transpose w. Both the two matrices are symmetric and positive semi-definite, since the Laplacian matrix L and the diagonal matrix D are both symmetric and positive semi-definite. And if you still remember linear algebra, when these two matrices are symmetric and positive semi-definite, that means the eigenvalue is always larger or equal than 0. Okay. So how can we learn the Laplacian phase for phase representation? In the formulation, because xd x transpose is singular, so this is a problem similar to the feature phase. Okay, if this matrix is singular, then it will cause the difficulty to find the eigenvalue. Okay, so we need to first project the image set into a PCA subspace, so that the resulting matrix is non-singular. Okay, it's also for noise reduction, and we have also seen this solution from feature phase before. So the algorithm to find the Laplacian phase is that we first do PCA projection. So we project the image set Xi into the PCA subspace by throwing the smallest principal component. And when we reduce to the theoretical useful subspace, we can construct the nearest neighbor graph. Okay, and then put an edge between node I and j if xi and sa are close. Okay, that means if they are close, they have similarity value. Otherwise, they don't have similarity. Otherwise, they don't have similarity value, or their similarity is zero. The constructed graph is an approximation of the local manifold structure. So by this way, we can avoid to describe all sample points, no matter how far they are. We avoid to make projection by linear transformation. In a locality, in a neighborhood, they may be described in a linear way. However, when we consider all the sample points, they are described by a local manifold structure. The third step is to choosing the weight. Okay, so we need to define the similarity matrix, and then we find the eigenmap. Okay, so we need to solve the generalized eigenvalue problem. Okay, and find the best the best projection vector W0, W1 to WK minus 1, and the order according to their eigenvalue. Okay, and because as we said before, both these two matrices are symmetric and positive semi-definite. Therefore, the eigenvalues are always larger or equal to 0. Okay, and if we sort them, then we can pick the largest largest k eigenvalue, and then we get the largest k eigenvector. Okay, and these eigenvalues are equal to or greater than 0 because these two matrices are symmetric and positive semi-definite. So finally, overall, given a phase image X, we map this X into Y by this matrix. And how can we find this matrix W? Actually, this matrix consists of two parts. The first part is a PCA matrix. The second part is a LPP matrix. Okay, so Y is a k-dimensional vector that is a projected sample point, and the W is the transformation matrix. And the column vector of W are the so-called Laplacian phase. Okay, why it is called Laplacian phases? Because in solving the optimization problem, there is a Laplacian matrix in the middle of the objective function. In this paper, the author showed the power of manifold analysis by this example. They use around 2,000 phase images with 560 dimensional, represented as a 560 dimensional vectors. And then they use 10 samples for testing and 9055 for training. And this figure shows the when we map high dimensional facial images into a two-dimensional space and by LPP, and then the mapping makes the neighboring points in the image space nearer in the phase space. Okay, that is, we can observe that at the depth part, the phase images with closed mouths. So we can roughly see that the data points can be separated into the left part and the right part, and at the depth part, it consists of phase images with closed mouths, and on the right part, it consists of phase images with open mouths. And at the bottom part, we can see around at the bottom the points along the right path. Okay, that is if we go from this point to this point, and if we show uh, all the sample points that this pass through, then we will see that we will see this sequence. So from top to bottom, we see that the viewing angle is different. Okay, from the left face to the right face of this person. Okay, so through this example, we can see that the LPP can more appropriately describe the geometric structure or the high-dimensional structure of the visual face of face images. Okay, and such formulation can describe the difference of different facial expression, either open mouth or closed mouth, or different viewing angle from the left face or to the right face, and so on. And this figure shows the 10 testing samples. So some of them are at the top part, and some of them are at the bottom part. And some of them are open mouth, and some of them are closed mouth. And this test sample optimally find their coordinate, which reflect their intrinsic property, like different pose and expression. The figure shows the first 10 eigenface, visual face, and the Laplacian face from the face images in the Yale database. We can see from the eigenface, we can obviously see the important variation from different facial parts. Okay, and from visual face, it just looked like noise. Okay, with rough face contour. Okay, and it is a similar case in the Laplacian face. Although this visual face and Laplacian face are not much like the face image. However, the combination of this visual face or Laplacian face are more appropriate to describe face images and facilitate more accurate face recognition. So in the evaluation, they use the three databases, including Pi from CMU. Pi is pose, illumination, and expression. Okay, L database and the MSI database. Okay, and before doing modeling and testing, they do some pre-processing like locate face, normalize, do some normalization such that two eyes were aligned at the same point position, and the face area are cropped into the final images for matching. So we just do alignment and normalization and just crop the region from the eye to the button of mouse. Okay, so we use the closely cropped face, and each image is 32 by 32, and thus 1024 dimensional. And then they use nearest neighbor classifier, and the Euclidean matrix is used as the distance measure to construct the neighboring graph. Okay, 4 or 7 nearest neighbors are set according to the size of the training set. From the Yale database, okay, a random subset with 6 images per individual were taken to form the training set. And this table shows the experimental result. We can see that first we search the best number of eigenface, visual face, and Laplacian face to do the performance comparison. Okay. So this figure shows when this figure shows the relationship between error rate and the dimension to represent the face image. Okay, and we just pick the best dimension to show the performance of eigenface, feature face, and Laplacian face. So the best dimension for eigenface is around 33, and the error rate is 25%. And for feature face, because feature face has a theoretical limit, so the dimension is fixed, and the error rate is around 20%. Okay, and for Laplacian face, the minima error rate can be reduced to 11%. Okay, so in general, the performance of the eigenface and the Laplacian method vary with the numbers of dimension. So we just compare them with their best cases. And for the PIE data set, there are 68 subjects with more than 40,000 face images captured by 13 synchronous cameras and 21 flashes under various pose, illumination, and expression. So this is a very challenging data set. Okay, we can see some sample images here. So they have significant illumination change and pose variation. And there are 170 face images for each individual. These are used in the experiment. Okay, and 85 of them are for training, and the other 85 are for testing. Okay, and here is the performance based on the PIE dataset. Okay, as we expect, when the dimension of reduced space increase, the error rate also decrease. Okay, the error rate decrease, and the best performance of eigenface is around 20% error rate, and for feature face it's around 5.7%, and for Laplacian face it's around 4.6%. Okay. In this case, feature face perform comparatively to the Laplacian face, while eigenface perform poorly. Okay, the error rate of Laplacian face method decrease fast as the dimensionality of the face subspace increase. Okay, so as we increase the dimensionality of projected space, the error rate decrease quickly. Okay, so in this case, the performance of feature face and Laplacian face are comparable. However, the dimension of Laplacian face is much higher than feature face. So we can say that from the PIE database, Laplacian face does not significantly outperform feature face. Therefore, the author also performed experiment based on the MSIA database. In this database, there are 12 individuals captured in 2 different sections with different background and illumination, and 64 to 80 face images were collected for each individual in each section, and all the faces are frontal. So one section are for training and another one are for testing. And this is the relationship between error rate and the dimension of projected space. We can see that in this case, in this database, the Laplacian face outperform feature face significantly. Okay, not to say the eigenface. Okay, so right now the error rate of eigenface is 35%. The error rate of feature face is 26%. When we use Laplacian face, the error rate can be reduced to 8.2%, although the dimension of Laplacian face is still much higher than the feature face, but we got significant better performance. When we do training and testing, we often expect that a good algorithm could be able to take advantage of more training sample. Therefore, in this paper, they design an experiment that 10%, 40%, 70%, and 100% face images were randomly selected from the MSRA Section 1 for training, and try to evaluate when we change the numbers of training data if the performance change. Okay, and this algorithm aims at discover face manifold, and more training sample help to recover the manifold structure. Okay, so this table shows the performance when the numbers of training data increase. The error rate of Laplacian phase and eigenphase decrease. Okay, so we can see the eigenphase, the error rate is from 46% to 35%, and the Laplacian phase changed from 26% to 8.1%. Okay, so eigenphase also take advantage of more training data. However, for feature phase, no convincing evidence shows that it can take advantage of more training data. So this is one way. This is another way to show the superiority of Laplacian phase over feature phase. So finally, we have introduced three important face recognition approach. The first one is eigenphase, second one is feature phase, and the third one is Laplacian phase. And the face recognition are actually very hot topic for many decades. Until today, still many researchers work on face recognition, and newer technology has been proposed in recent years. So if you are interested in face recognition, you can read the literature. After year 2005, there is a very famous approach based on sparse coding, and right now many face recognition method were proposed based on deep learning. So this is a very large, this is a very big research field, and many researchers have put many efforts in recognizing face.